Okay, let's move on. In the last class, we started to discuss crystalline covalent organic frameworks, and this class of crystalline porous materials is the latest class of materials, was discovered just about 15 years ago. And the first material that was discovered was this boronic acid anhydride COF. We discussed it already in the last class, and I just briefly review this. And this boronic acid anhydride covalent organic framework is prepared from a single precursor, this boronic acid, just by polycondensation. Okay, so as the polycondensation proceeds, water is being eliminated, but by clever choice of the reaction conditions, the water concentration is kept at a level that on the one hand side still keeps the framework interconnected without depolymerizing it. So you're not going too far in the reverse direction. But on the other hand, we have enough water as a mineralizer available to labilize the boron-oxygen bond. Okay. So even though the boron-oxygen bonds are not dative bonds in the classical sense, like it is the case in metal organic frameworks, we can still labilize the boron-oxygen bond, okay, through hydrolysis. So you need to imagine that there is a nucleophilic attack of that water on that boron here, okay, which is electron deficient, and that then can cleave a boron-oxygen bond, okay? But of course, that process is reversible. The boron-oxygen bond can also reform, okay? So through this process, we can achieve a thermodynamically controlled reaction that eventually leads to a crystalline product. And the structure of this crystalline product is fairly predictable because of the directive nature of the covalent bond. Okay, so this COF material was the first material that was discovered. And from that point on, many others followed. So in addition to making anhydrides of diboronic acid, one can also polycondense boronic acids with orthohydroxy phenolines, which are multitopic. Okay, so again, one can extend simple molecular organic chemistry to extended solid state chemistry. Okay, so at the molecular level, we can perform a reaction which is shown here. So you can take a simple boronic acid like this phenylboronic acid and condense it with this hexahydroxytriphenylene unit, okay, which has three pairs of hydroxy groups here in ortho position. If you choose the molar ratio 3:1, okay, then well, we will react all these OH functionalities and we will get this boronic ester molecule here. Okay. So now again, if we just replace this monoboronic acid by a diboronic acid, we will get a framework material because we now connect a ditopic unit with a tritopic unit that naturally leads to a two-dimensional extended solid with a sheet structure, and that which is now shown here. Okay, and you see that in this two-dimensional extended solid, we have the diboronic acid units shown here, interconnected via this tritopic linker here, okay, to make these hexagonal pores. Okay, and these hexagonal pores are now larger in comparison to the boronic acid anhydride COF. Okay, they're actually already in the mesoscopic size. You see, they are 27 angstroms or 2.7 nanometers. Remember, the mesoscopic range starts at 2 nanometers. Okay, so also this can crystallize fairly easily because the boron-oxygen bonds that form that are part of the ester bonds are labilized through the presence of water, which is present in the reaction mixture at the right concentration. Okay, again, that's tunable between the by adjusting the ratio of the liquid phase in comparison to the gaseous phase. Okay, so again, the water can well make a hydrophilic attack on the boron-oxygen bond, thereby cleaving the boron-oxygen bond, and that process is reversible. Okay, so these kinds of covalent organic frameworks are the materials with the lowest density known. Okay, because they only contain elements of the second period of the first and the second period of the periodic table: hydrogen, oxygen, carbon, and boron. So they're even lighter than metal organic frameworks, which typically include a transition metal, which is relatively heavy. They're also lighter than zeolites, which contain silicon, which are relatively heavy and who do not have atomically thin pore walls. So these covalent organic frameworks are the record holders in terms of lowest density. Okay. So now, how stable are these materials? So neither the boronic acid anhydride COFS nor their esters are particularly stable. Stable, I mean here chemically stable. So actually thermally fairly stable up to 400 degrees Celsius. But if you expose them to air, they collapse quickly. And why is that? Well, air contains moisture, okay? And that moisture can relatively easily hydrolyze these ester bonds here and can relatively easily hydrolyze the boronic acid anhydride units as well. So again, you see here that the liability of the bonds, which allows you to achieve the crystallinity of the material, has the drawback that the chemical stability is not of these materials is not particularly high. Okay. However, meanwhile, other covalent organic frameworks are available, which are not based on boronic acid chemistry, which are significantly more stable, and we will discuss these in a moment. But before we do that, I wanted to mention also that these boronic acid-based covalent organic framework can also be extended from two-dimensional frameworks to three-dimensional frameworks when you actually switch from diboronic acids to tetraboronic acids, as it's shown here. Okay, so here you have a tetrahedral building unit in which you have a carbon in the center, okay, or a silicon in the center, and then that carbon and that silicon respectively is surrounded by 4 phenolene units in a tetrahedral fashion, which have here 4 boronic acid units in para position. Okay, and if you then polycondense this kind of molecule with hexahydroxy triphenylene as before, then you can achieve the formation of a three-dimensional covalent organic framework, which has a 3-4 connectivity. Okay, so you interconnect these tetrahedral building blocks with trigonal planar building blocks. So when you use hexahydroxytriphenylene as a unit, then you will have here this hexahydroxytriphenylene as a tritopic linker. If you use this tetrahedral building block alone and you form the anhydride, then you have these B3OC 6-membered ring as the trigonal planar building unit. Okay. Nonetheless, you can produce different structures. Okay, so even though both reactions connect the tetrahedral unit with the trigonal planar building unit, the resulting structures are not identical, and you see this here. So, in the case of the boronic acid anhydride, we have a framework structure with a framework typology CTN. So these 3 letters are actually in an analogy, shows an analogy to the code used for zeolites, even though these types of structures do not appear in zeolite chemistry. Cannot, because we use fundamentally different building units, while when you use hexahydroxytriphenylene, you are arriving in this framework topology, which is named BOR. Okay. So you see here the 2 different structures. We do not need to discuss them in detail here. The only thing that we should remember here is that they are both 4-3 interconnected frameworks, but there are several possibilities to realize 4-3 interconnected frameworks, and which one is energetically minimized depends on the exact building blocks. Okay, so when we have here these B3O3 6-membered rings, the CTN structure is energetically favored. If we use this hexahydroxytriphenylene, then the BOR structure is energetically favored. Okay. Again, these structures, 3-dimensional structures, have extremely low density. They have also extremely high surface areas, but they are chemically not very stable, especially they're not very stable in moist air to water hydrolysis. Therefore, after the discovery of these first covalent organic frameworks, have looked for other ways to interconnect building blocks that lead to more stable covalent organic frameworks. In one class of quite stable covalent organic frameworks are triazine-based covalent organic frameworks. And these covalent organic frameworks have a triazine unit, as you see here, composed of 3 nitrogens and 3 carbons that are interconnected by rigid organic groups. Okay, so these covalent organic frameworks can be prepared from nitriles. So when you start out with this 1,4-dicyano-benzene, then in molten zinc chloride at approximately 400 degrees Celsius, these cyano units, they trimerize, okay? But because of the high temperature and the presence of this Lewis acidic zinc 2+, that trimerization reaction is sufficiently reversible, yeah, so that the system can crystallize, okay, to form this structure here, okay. But for that formation of that structure, we need much harsher conditions. Molten chloride and 400 degrees Celsius, okay? Whereas the boronic acid-based framework can be prepared at much milder conditions, typically at temperatures of around 100 to 150 degrees Celsius, okay? But once that crystalline organic framework here has been formed, and you just cool this down to room temperature, and you just dissolve your zinc chloride by in water, okay, you have a chemically quite stable structure, okay. So these carbon-nitrogen bonds, they do not hydrolyze under ordinary conditions. So there's a catch to that, though. This kind of chemistry, the trimerization of nitriles, is not as versatile as the polycondensation of boronic acids in terms of the ease with which crystalline structures form. Okay, so on a sheet of paper, you could very easily imagine that this chemistry would extend to many other structures. For instance, we could replace this phenylene unit here just by a diphenylene unit and do exactly the same reaction. And in principle, the same reaction works, but it has been found that whatever conditions you try, the stuff doesn't crystallize. Okay, so this is generally still an issue with covalent organic frameworks. The crystallization of these frameworks is not very predictable often. And even if you make just a small variation to your reactants, and you can easily draw an analogous crystalline framework on the sheet of paper, not necessarily that crystalline organic framework will form. So oftentimes you arrive at amorphous structure, okay, no matter how hard you try to vary the reaction conditions, okay. So this is true for this class of triazine covalent organic frameworks. So even though there have been intense efforts made to make many other structures of this kind, because they're attractive due to their chemical stability, to my knowledge, this is the only case in which this has been succeeded. So this is, to my knowledge, still the only example of a crystalline triazine-based covalent organic framework. It's not so difficult to make amorphous ones with other building units. All right. So another class of covalent organic frameworks, which is also fairly stable, but has been proven to be more versatile in its chemistry, are so-called imine-based, or sometimes also called Schiff-based covalent organic frameworks. So these rely again on a organic reaction, which has been well known for actually many decades, but just fairly recently has been extended in order to form crystalline organic frameworks. Okay. So from organic chemistry, we know that when we react a primary amine with an aldehyde, then under the elimination of water, we are forming what is called a Schiff base, or also called an imine. Okay, so essentially, mechanistically, this nitrogen here has an electron lone pair, which is a nucleophile. Okay, so that electron lone pair actually attacks here at this carbon atom. Okay, so that carbon oxygen bond becomes a carbon oxygen single bond. A proton actually migrates from the nitrogen here to this oxygen, and then formally water is getting eliminated under the formation of a nitrogen carbon double bond. Okay, so this process or this reaction is also reversible in principle. So you can take a imine or Schiff base, and with sufficient amount of water, you can actually hydrolyze that Schiff base in order to make the amine and the aldehyde. Okay, so the amount of water in the reaction system decides whether the chemical equilibrium lies more on the right side or the left side. Okay, so now I can again use this principle in order to produce a covalent organic framework. It's just again that you have to go from monotopic building units to multi-topic building units. Okay, so for instance, you can use a tetrahedral tetratopic building unit, such this one here, where we have again a carbon in the center, 4 phenyl groups around, and 4 amine groups in the para positions at the phenylene rings. And then react this with a dialdehyde, the 1,4 dialdehyde, as a linear building unit. Okay, and then you basically interconnect via the nitrogens at the tetratopic building unit with that phenylene ring here. Okay, and of course that reaction proceeds in all 3 in all 3 dimensions. Okay, now when you essentially interconnect a tetrahedral building unit with a linear unit, then the most simple structure that you can form is a diamond structure. Okay, because remember, in diamond we have carbon atoms, okay, which have an sp3 hybridization, which are just directly interconnected with other carbon atoms that also have an sp3 hybridization and are tetrahedrally surrounded. Okay, so when you polycondense building units like that here, you are also forming a diamond framework. It's just that it's an expanded version of a diamond framework with a large degree of porosity in between the tetrahedral building units. Okay, so these diamond-like networks have also the property that they tend to form interpenetrated structure. So they actually allow the formation of a second diamond network to grow within the first diamond network being formed. And the driving force for that is that nature tends to avoid porosity. Nature tries to fill space as good as possible. So in a sense, the first interpenetrating framework, the first framework acts as a template for the second one. And if there's enough space, you can even grow a third one, a fourth one, a fifth one, and so forth. So in the case of this structure, we have actually an extreme case. We actually have 7 diamond-like networks that interpenetrate each other in order to fill space most effectively. Okay, so this kind of chemistry is fairly versatile. it not only works for that particular reaction of this tetratopic amine and this ditopic aldehyde, it extends also to many other building units. For example, one can also make two-dimensional imine-linked covalent organic frameworks. What would you need to do? Well, you would need to replace this tetratopic building unit, which is tetrahedral, by tritopic one as planar. Then you will interconnect a planar tritopic building unit with a planar ditopic one, and that will give you, again, a two-dimensional extended solids. So this kind of chemistry can be done also at relatively mild temperature conditions with the right amount of water in the reaction system. Despite that, the respective imine-linked covalent organic frameworks, they are pretty stable to hydrolysis. Okay, so they're definitely air stable. Okay, so ordinary moisture in the air cannot hydrolyze these imine links easily. You would need more drastic hydrothermal conditions in order to drive the chemical equilibrium to the right side. So in this case, naturally the chemical to the left side. So in this case, naturally the chemical equilibrium lies more on the right side, therefore the higher hydrothermal stability. Okay, so these are the imine-linked covalent organic frameworks, and the latest discovery is actually all carbon interconnected covalent organic frameworks, which are crystalline. So you would imagine a carbon-carbon bond actually to be a pretty inert bond and a little Laber bond, but certain reactions that involve the formation of carbon-carbon bonds are actually reversible. So that means that the carbon-carbon bond can be formed and cleaved reversibly, which then allows also the crystallization of COFS with all carbon interconnected covalent organic frameworks. In such a reaction is the so-called Knover-Nagel condensation reaction, also a reaction that has been known for a long time in organic chemistry, but it's been just recently discovered for making extended solids. So essentially here you react an aldehyde, so in this case a tetratopic aldehyde, which is planar, it's a square planar building unit, with a nitrile that has a CH2 group in between the nitrile unit and the phenyl unit here. So this nitrile unit here is a quite electron withdrawing unit, and for that reason the carbon-hydrogen bond of the CH2 groups here are somewhat acidic. Okay, and because of that this CH2 group is actually a nucleophile. Okay, so it can actually attack here at this carbon here, which has a high delta plus to it because of the electron withdrawing oxygen group here. And that's the driving force for formation of the carbon-carbon bond. Okay, the formation of this carbon-carbon bond will lead to the elimination of water, which will lead to another carbon-carbon bond, so that we have essentially, well, a carbon-carbon double bond that forms upon the elimination water. Okay. So that kind of reaction can occur with both at both ends of this diatopic unit and at the 4 reactive positions of this tetratopic aldehyde here. So that we basically form essentially a 2-dimensional square framework, okay, in which we have now a completely conjugated system of carbon-carbon double bonds, okay. Of course, you still have your nitrile units attached to that backbone of carbon-carbon double bonds as well. Okay. So here are the typical reaction conditions at which this framework forms. So it forms in a mixture of mesitylene and dioxane in the presence of 4 molar sodium hydroxide. Okay. Reacted for 3 days at 90 degrees Celsius. And if you just react this mixture long enough, then you will get this covalent organic framework here precipitating out of the solution. Okay. So in this case, we get a microporous framework with a pore size of approximately 1.9 nanometers. And we have a surface area of 692 square meters per gram in this case. So such a structure is interesting from an electronic point of view because you have a fully conjugated pi system of carbon atoms. So this material is actually a relatively narrow band gap semiconductor, which is a band gap of 1.9 volts. In pristine state, the electrical conductivity is quite small. It's 6.1 times 10 to the minus 14 Siemens per meter. But after the oxidation with iodine, the electrical conductivity increases by many orders of magnitudes to 7.1 times 10 to the minus 2 Siemens per meter. So an interesting research direction in this field is actually to further narrow the band gap and to make all carbon interconnected COFS which are eventually metallically conducting. But to my knowledge, this hasn't been achieved this far, primarily because thus far no synthetic routes have been found in which you interconnect the building units not by simple carbon-carbon double bond, but by multiple carbon-carbon double bonds. Or in other words, to make actually really a fully interconnected ring system in which the rings are not interconnected by simple carbon double bonds, but in which they actually fused together. Okay, so these formal single bonds here are still responsible for why we have a relatively large band gap and we have a relatively low electrical conductivity. Okay, now all COFS that we have discussed thus far are crystalline, but they cannot be obtained in a single crystalline form. This is a big contrast to the chemistry of metal organic frameworks, which can be easily obtained as single crystals, and then this crystal structures can be relatively easily determined by X-ray diffraction. So the reason why metal organic frameworks form single crystals so easily is because the dative bond, metal ligand dative bond, is so easily reversible. So in the covalent organic chemistry, the bonds are still reversible, but not as easily reversible. And that leads to the fact that the crystals tend to be smaller. Okay, and you get crystalline materials, but your crystal sizes are not large enough so that you can do single crystal X-ray diffraction analysis. Okay, so that's another limitation in this field. So if you want to find out about the structure, you have to rely on powder X-ray diffraction data, and it's much harder to determine the crystal structure from powder X-ray diffraction data because, as we discussed earlier in the course, we have a two-dimensional projection of the three-dimensional reciprocal space when we analyze the X-ray diffraction data. So we lose information, and that makes crystal structure determination harder, and we are restricted to more simple structure. So to some extent, the directed nature of the covalent bond helps us because it actually allows us to predict structures, to just draw the most simple structures on a sheet of paper, then simulate the X-ray diffraction pattern, and then just see if that simulated X-ray diffraction pattern is in accordance with the experimental X-ray diffraction pattern that we measure. So this is often the method how the X-ray diffraction patterns of covalent organic frameworks are being analyzed. So because of the relatively high complexity of the covalent organic frameworks, the direct methods to determine the location of the atoms in the unit cell is not possible, okay? But by simple comparison between a simulated X-ray diffraction pattern of an assumed structure and the experimental X-ray diffraction pattern, one can prove that a certain structure has been formed. So nonetheless, it would be very desirable if you could also produce COFS in single crystalline form, because then one could easily analyze these single crystals by single crystal XRD. In a few cases that has been succeeded, in cases in which the covalent bond formed between the building units is particularly liable. All right, and the first example for which that has been demonstrated is actually shown here. So here you have a so-called hydroxylamine, which is tetratopic, okay? And one can actually oxidize this hydroxylamine to form here these nitroso groups using silver carbonate. Okay, and then these nitroso groups, they have the property that they can easily dimerize. You know that a simple NO molecule can easily dimerize to form N2O4, and that reaction is fairly reversible. And similar, these organic nitroso compounds can easily dimerize in a reversible fashion. Okay, and when you have a tetratopic linker, then you form a three-dimensional network in which basically your building units are interconnected by nitrogen-nitrogen double bonds, but that nitrogen double bond is fairly liable. For that reason, you can achieve crystallization fairly easily, and you can even grow large single crystals. And you see them here under the light microscope. And these crystals are then large enough so that you can analyze your covalent organic framework using a single crystal X-ray analysis. All right. Thus far, we have discussed all neutral frameworks, but one can also make covalent organic frameworks with both negative charges and also positive charges. And I wanted to illustrate this here by a few examples also. So here in this example, which was actually the first example of an anionic COF, first a macrocycle is being formed. See an organic macrocycle, rigid organic macrocycle, which forms from this alkyne, ditopic alkyne, through an alkyne metathesis reaction, okay, using an alkyne metathesis catalyst. And you get this square cycle here in pretty high yields. So you see that here at the corners of that square, we have these groups R, and these groups are nothing else but acyl groups. And then what you can do is actually hydrolyze these acyl groups and react the respective OH groups with boron trimethoxy ester in the presence of a base as a catalyst. Okay, and then you interconnect these squares here, okay, with BO4 linkages. Okay, so the boronic acid can now make 4 bonds to two different squares, okay, here and here, and these two squares then stand perpendicular to each other, okay, just because of the tetrahedral coordination of the boron. Okay, so that tetrahedral edge here and that tetrahedral edge, they stand perpendicular to each other, so that you're actually forming a three-dimensional anionic framework of interconnected, boron interconnected rigid organic macrocycles as shown here. Okay, so this framework is anionic because the boron is having a formally negative charge because it's tetrahedrally coordinated. Okay, you see that it's surrounded by 1, 2, 3, 4 electrons. And that's one more that the boron needs in the neutral state. So there are also organosilicate anionic COFS. Meanwhile, so again, we can extend here known molecular chemistry to COF chemistry. So when you react catechol with tetramethoxysilane or simply SiO2, then you're forming this anion here, in which you have silicon octahedrally coordinated by these oxygen atoms, which belong to these 3 different catechol units, and that reaction can proceed base catalyzed in an organic solvent like methanol, so for example, using lithium methoxide dissolved in methanol. All right, so now you can extend this chemistry by going again from a monotopic linker to a ditopic linker here. So you see we have here now 2 hydroxy groups at this end and 2 hydroxy groups at that end. And now when we react this molecule with tetramethoxysilane under similar conditions, in this case, lithium, sodium, or potassium methoxide in methanol at 180 degrees Celsius for 4 days, then in this case base catalyzed, we form this structure here of 6 membered rings, which is anionic because of the octahedral coordination of the silicon. Okay, the silicons have 2 negative charge, and then these 2 negative charges must be charge compensated by metal ions. Depending on the catalyst that you're using, this is either lithium plus, sodium plus, or potassium plus. Okay, you see here that you need fairly drastic